This video contains the solutions to the chain rule practice problems. Note that if you just stumbled upon this video using a search, this is the chain rule in multivariable calculus, not the chain rule that you would see in Calculus 1. So for this first problem, we want a formula in terms of t for dz dt, where z is a function of x and y are functions of t. So the idea here is that we can draw our tree to figure out what we want to do. So z is a function of x and y. So we start with z at the top, and then we draw little line segments down to x and y. Now x is a function of t, and y is a function of t. And so at each of these stages we can think of, this would be a partial derivative, del z del x, and this would be a standard derivative, dx dt. This would be a partial derivative, del z del y, and this would be a standard derivative, dy dt. As the chain rule would tell us that dz dt is del z del x multiplied by dx dt plus del z del y multiplied by dy dt. So what's del z del x? Well, that's the partial derivative of z with respect to x, which is going to be 2xy minus 4y. dx dt, well, x is t squared, so dx dt is 2t. Del z del y, that's going to be x squared, and then minus 4 times x. And then dy dt, y is 2t, so dy dt is 2. Now we're asked for a formula in terms of t, so this expression that we have that has x's and y's and t's in it is not really what we want. But the good news is that all we have to do is replace the x's and the y's by what they're equal to. So all the x's turn into t squareds, and all the y's turn into 2t's. So 4 times 2t times 2t, and then x is going to be t squared minus 4 times t squared, and that's going to be times 2. And then we can simplify this. So we get 4t cubed minus 8t, all multiplied by 2t, and then t to the fourth minus 4t squared multiplied by 2. So that's going to be 8t to the fourth minus 16t squared plus 2t to the fourth minus 8t squared. That's going to be 10t to the fourth minus 24t squared. And that's our expression. Similar problem here. Here we want a formula in terms of t for dw dt, where w is x, y, z, and then x and y and z are given here. So again, we can draw our tree. We start with w at the top. W is a function of x and y and z, so we have 3 line segments coming down. And then each of x, y, and z are functions of t. So that gives us 3 partial derivatives, del w del x, del w del y, and del w del z. And then 3 more derivatives, dx dt, dy dt, and dz dt. So that means that the derivative we're looking for, dw dt, is going to be del w del x times dx dt plus del w del y times dy dt plus del w del z times dz dt. And now we just start filling these things in. So w is x, y, z, so when we take the partial derivative with respect to x, the derivative of x is 1, and yz is a constant multiple, so we just get yz. Multiplied by dx dt, well, the derivative of 2t is 2. The derivative of w with respect to y is xz, and then the derivative of t cubed is 3t squared. And then finally, the derivative of w with respect to z is xy, and the derivative of the square root of t is 1/2 t to the minus 1/2. And now we're just going to substitute in. So y was t cubed, z was the square root of t, multiplied by 2. xz, that's going to give me 2t times the square root of t, times 3t squared. And then xy, that's going to be 2t times t cubed, and then that's multiplied by 1/2 t to the minus 1/2. All right, so t cubed times the square root of t, that's going to be t to the 7/2, multiplied by 2. T times square root of t times t squared, that's also going to be t to the 7/2. 2 times 3 is 6. And then here, once again, we're going to get t to the 7/2, and then 2 times a half is 1, so that's just t to the 7/2. And then 2 plus 6 plus 1 is 9, so we get 9 times t to the 7/2. All right, now we start getting into what this chain rule might actually help us do. Because in the previous problems, we could have just substituted those formulas into the main function and just taken a derivative like we would have back in Calc 1. So here's a situation where we wouldn't necessarily be able to do that. So we have our formula for a right circular cylinder, and we're told that the radius is 2 centimeters and increasing at a rate of 0.4 centimeters per minute. So when we say that the radius is increasing at a rate of 0.4 centimeters per minute, what we're saying is that dr dt is 0.4. And then when we say that the radius is 2 centimeters, that means that r at this moment is equal to 2. Similarly, the height is 5 centimeters, so that means that h is going to be 5 at this moment, and decreasing at a rate of 0.3 centimeters per minute. So that's going to tell us that dh dt is equal to negative 0.3 because it's decreasing. And we want to know the rate at which the volume is changing. But volume is a function of r and h. And r and h, as we're being shown here, are functions of t. Which means we can use the chain rule. Del v del r multiplied by dr dt, and then del v del h multiplied by dh dt. Add those together, and that's going to give us dv dt, the rate at which the volume is changing with respect to time. So del v del r multiplied by dr dt plus del v del h multiplied by dh dt. Okay, so del v del r, we're going to look at the formula for our volume, which is up here. Del v del r is going to be 2 pi r h. Dr dt, they tell us in the problem, is 0.4. Del v del h, taking the derivative partially with respect to h, just gives us pi r squared. And then dh dt, again, they tell us in the problem, is negative 0.3. Now we're going to plug in the values they give us. So they told us r is 2 and h is 5, so that gives us 2 pi times r, which is 2, times h, which is 5, times 0.4, plus pi times r, which is 2, multiplied by negative 0.3. And that's going to give us 6.8 pi, which is approximately equal to 21.36, and this would be cubic centimeters per minute. So here we have a function w of the variables x, y, and z, and then x and y and z are each themselves functions of s, t, and r. So what we have is a slightly more complicated tree structure. So we have w here at the top, and then we have x and y and z. And then x and y and z are each functions of r, s, and t. So what we want is del w del t. So we want to focus on the t's here. So that's where we want to get to. We want to get from the top of our tree here down to the t's. So we're going to need del w del x and del x del t, del w del y and del y del t, and then del w del z, and then del z del t. So del w del t will be the products, the sum of those products. So that's going to give us this expression. All right, so now when we take the derivative of w with respect to x, actually when we take the derivative of w with respect to any of these variables, we're going to get a very similar expression each time. It's going to be 1/2 times the quantity x squared plus y squared plus z squared to the minus 1/2, and then multiplied by the derivative of the inside. The first time, when we take the derivative with respect to x, we get 2x. Derivative of y squared will be 0, and the derivative of z squared will be 0. Now del x del t, since x is st, that's just going to be s. Now when we take the derivative of w with respect to y, we get 1/2 x squared plus y squared plus z squared to the negative 1/2, and then multiplied by the derivative of the inside, which this time is 2y. Now the derivative of y, which is rs with respect to t, well, that doesn't have any t's in it, so that's going to just be 0. And then finally, the derivative with respect to z is going to be 1/2 x squared plus y squared plus z squared to the minus 1/2 times 2z, and then multiplied by the derivative with respect to t, which is going to be r. So this middle term cancels out. So that's gone. And then we can factor out the common factor here, which is going to be the 1/2 x squared plus y squared plus z squared to the minus 1/2. And then what that leaves us with is 2xs plus 2zr. Now the 1/2 is going to cancel out with those 2's. And so we just end up with xs plus zr, all divided by the square root of x squared plus y squared plus z squared. Now, we're being asked for a formula in terms of r, s, and t, which means we're going to need to substitute in what x, y, and z are. So x is st, so on the top that gives us s squared t. Z is rt, so that's going to give us r squared t. And then on the bottom, we're just plugging into those x squared, y squared, and z squared. So that's going to be st squared plus rs squared plus rt squared. And that is our final answer. One other application that we can use for this chain rule is to find the dy dx for just an equation with two variables. We did know how to do this back in Calc 1 using implicit differentiation, but it turns out that partial derivatives gives us another way to think about it. But the partial derivative formula that we're going to use requires us to have something that looks like capital F of xy equals 0, which means I'm going to manipulate this equation so that it has a 0 on one side. So I'm going to subtract y over x from both sides. That's going to give me x plus y cubed minus y over x equals 0. And then what the formula tells me is that dy dx is going to be negative the x partial derivative of capital F divided by the y partial derivative of capital F, where this thing here, that's my capital F. Okay, so what's the x partial derivative? Well, the x partial derivative of x is 1. The x partial derivative of y cubed is 0. And then yx, we can think of y over x, we can think of y times x to the minus 1. And so the derivative of that with respect to x is minus y x to the minus 2. And then the partial derivative with respect to y, that's going to be 0. The derivative of x is 0. Y cubed is going to give me 3y squared. And then the derivative of y x to the minus 1 is just x to the minus 1, because the derivative of y is 1. Now this is a little bit messy and we can clean it up. So when we distribute that negative, we get minus 1 plus, and I can write that as y over x squared. And then on the bottom, I get 3y squared minus 1 over x. We don't really usually like having fractions within fractions like that, so I'm going to multiply top and bottom by x squared. That's going to give me negative x squared plus y on the top, and 3x squared y squared minus x on the bottom. And that would be my implicit expression for my derivative of y with respect to x.